So on symmetric key encryption, we introduced some notation and then said, for example, that we'll assume if we decrypt the ciphertext with the correct key, we'll get the original plaintext. That's the assumption about the algorithm. And that the decryptor will be able to recognize the plaintext is correct. And sort of the opposite, if you decrypt the ciphertext using the incorrect key, we will not get the original plaintext. And the decryptor will be able to recognize that that key is wrong because it's not the, it's random looking plaintext, unrecognizable. We're going to go through these assumptions and some others and see how they we use them to provide the feature or the services of confidentiality and authentication and integrity. The assumptions are spread through this handout. But if you scroll forward a few pages, you'll see that there's a page, or 2 pages that summarize all of the assumptions together. So you may want to refer to that. It's the same text, but just everything's combined together. And what we'll do today is look at how we use these assumptions to build up our cryptographic techniques for providing confidentiality, integrity, and authentication. So we may not use the slides much today. We'll draw some pictures and refer back to these assumptions. The first thing, a key security service is confidentiality. I send something to someone, an attacker intercepts that message. I don't want them to be able to read it. So we know we encrypt the message before we send it. We started to draw that yesterday, but I'll draw it slightly different. That is, user A and user B are the normal users. A's got some plain text, a message it wants to send to B. I'll denote it with the subscript T here, meaning the plain text that we're going to, we think, transmit, to send. We don't actually send the plain text though, we encrypt it. We obtain some ciphertext by encrypting using some key the plaintext. Where the plaintext, I'll denote as PT, is encrypted with a key and we obtain ciphertext CT. CT is the ciphertext we're going to transmit to user B. What's the name of the key we're going to use here? What subscript am I going to write for this example? Think about the notation we introduced yesterday. What's the subscript for the key? This is a shared secret key, a KAB. It's a key shared between user A and B. If user A wants to send a message to B, then they use the key shared between them and B. So I'll write the subscript KAB. So that's what we do before we send, and we transmit a message to B. What do we send to B? Well, we'll just summarise here, CT. Actually, I write it at the start. Say we transmit a message across a network or a communications channel from A to B, and we denote that as CT, that's ciphertext transmitted. And user B will receive that message. Now, for some later cases, I'll write this, what's received as CR. A little bit strange, but in this case, CT and CR are identical, they are the same. I transmit the ciphertext, it goes across the network, something's received by B. What is received by B? The transmitted ciphertext, except I've given it a different name. I'm going to say what's received is CR. In the normal case, they are identical. the ciphertext is transmitted and received, but later when we see some other attacks, they may be different. So I'll give them different names of what's sent and what's received. What B does when they receive a message, for confidentiality, they want to see the message, so they decrypt. And we'll write that we obtain PR by decrypting. What's the key we use to decrypt? KAB, it's a shared secret key. B receives a message from A, therefore we'll use KAB to decrypt. And they decrypt what they receive. And they get some value PR, the plain text received. In this case, we'll assume that there's no attacker in the middle at this stage. So CT and CR are the same. That is CT equal to CR? Yes, in this case. Later we'll see no. Just for this initial case, they're the same. So we could have written this equation instead of CR and PR, CT. Does PR equals PT? Does PR, the plain text received, equal the plain text transmitted? Yes. Why? Let's look at our assumptions. Yes, I think it's obvious, but let's make sure that our assumptions capture that. Decrypting the ciphertext, so assumption A6 on this list, the one at the bottom, decrypting the ciphertext with the correct key, the same key that was used for encryption, will produce the original plaintext. So that's the assumption that tells us that yes, the plaintext received will be the same as the plaintext transmitted. Our assumption, if we use the correct key, and we can see KAB was used to encrypt, KAB, the same key is used to decrypt. If we decrypt CR, which is actually the same as CT, we will get PR being the same as PT. We assume that's the case. That's the obvious case. We get the same plaintext back. So B gets the plaintext. What if, oh no, we'll see that in a moment. Let's see an attack. From confidentiality perspective, we now have a malicious user, and the malicious user in the middle, instead of C, calling him C, we'll call him Mao, the malicious user. Okay. Now, the malicious user, what do they know in this case? The attacker? Well, the things that they know, let's have a look at the list of assumptions. If we scroll down on the assumptions, we talk about what the attacker knows. It's on one of the slides as well. We assume that the attacker knows all the algorithms used. So they know what was used for encrypting and decrypting, whether it was DES, AES, or something else. We assume that, right, the attacker can intercept any message. A message was sent across the network. The attacker can get a copy of that message. They know C, CT or CR. They're the same in this case. The attacker does not know the secret values. In our case, they do not know KAB. We'll assume that they do not. All right, the last assumption is about brute force attacks. They can't do brute force attacks unless the length of the key is less than, I put a number here, less than about 80 bits. Now that's not precise, but assuming the key is long enough, they will not be able to do a brute force attack and discover the key. So the attacker knows the algorithms, they know the ciphertext, but they don't know the key. The malicious user in this case, they have, let's say CT, what was transmitted. It's also the same as CR. They know the encryption algorithm, the decryption algorithm. They want to find the plain text or the key. They can't guess the key because it's the length such that they can't do a brute force attack on. So what do they try to do? To get the plain text, what the attacker can try to do is decrypt using some key, CR, what key can they use to decrypt CR? Any key they like, except one. We'll assume that they cannot use KAB because they don't know KAB. Right? When I say any key, well, they can use a key, but we'll assume that they're not lucky and they can guess KAB because it's so long that the chance of guessing it is so small. So we'll assume whatever the key they try here, it is not KAB. Doesn't matter what we denote, K malicious, whatever key they choose, where the key they use is not equal to the KAB. That is, they don't know KAB. So if we decrypt the ciphertext using some key other than KAB, we get some plain text. The plain text the malicious user gets the question is the plain text the malicious user gets the same as the transmitted plain text? What's the answer? They decrypted the ciphertext using the key that they chose. The key that they chose is not the same as KAB. And they get some plain text as output. They apply a function, they get an output. Some plain text I denote as the plain text the malicious user gets. Is that value the same as what A started with? No, it's not. And that's one of our assumptions. A7, decrypting ciphertext using the incorrect key will not produce the original plain text. Okay, so we've used a different key, therefore we assume we will never get the same plain text. And in fact, the malicious user will be able to recognize that this is wrong. They will know that it's not the right plain text, but that's of no use to them. They want to get the correct one. No, it is not. Okay. This is just showing that we've achieved confidentiality. We've sent a message from A to B. B decrypted it and got the original plain text because they had the key. The malicious user that intercepts that ciphertext, even if they try to decrypt, they cannot get the original plain text because they don't have the key. So that's the concept there. Just showing how we apply those assumptions to show that that's true. Any questions on confidentiality? What does the attacker need to do to find the plain text? Get 2 copies. 2 copies of what? Right. in this case, we assume the malicious user only knew the current ciphertext and the algorithms. Maybe the malicious user has observed past communications and they've seen past pairs of past ciphertext messages, different ones, and somehow have managed to learn the corresponding plaintext values. And that's a common assumption in practical attacks, that the attacker, so this is a slight extension, the malicious user also knows pairs, like they know that in the past there was some ciphertext, some old ciphertext that was sent from A to B. They know it was encrypted with the same key, and they have also somehow discovered the corresponding plaintext. This is what we say is a known plaintext ciphertext pair. It's easy to get the old ciphertext values, just intercept many packets, many messages. But how do they get the old plaintext message? And they don't know the key? Maybe the message was released through some other means. Maybe the message was old and it was no longer needed to be kept secret. So therefore it was made public and the attacker learnt about that. Therefore the attacker now knows an old ciphertext value, an old corresponding plaintext value. They don't know the key to get from one to the other, but they know the pair. They could try to use that to help them find the key so that they can decrypt the new ciphertext value they've intercepted. So practical attacks may use past values to try and help. The secure algorithms, it still doesn't make it easy to find the key or to decrypt the ciphertext. So for AES, for example, there are no known attacks. Even if you have billions of past pairs of plaintext and ciphertext, it still doesn't help you to get back to the original one. So no, that doesn't help. We'll assume it does not help. Even if you know many of these, it doesn't help. So what will the attacker do to defeat the confidentiality service? Well, there's nothing they can do under the assumptions that we're working on. Assuming they can't find the key, right, and we assume that because it's long enough. I chose a key KAB which was long and random, so the only way for the attacker to find it is to guess it, and we know that it would take too long to try and guess that. So they can't find the key. Assuming the algorithm, the encrypt and decrypt algorithms are strong, there are no flaws in them, AES is considered like that, then there's no way for the attacker to find the plaintext in this case. And that gives us our confidentiality. That's why we consider this concept secure. Confidentiality is easy to provide, or compared to some other services. Use a strong encryption algorithm and use a large key. Right? But there are some practical problems of ensuring that the key is kept secret. If the attacker does find the key, we have a problem. We'll assume they cannot. Another service that we'd like to provide, or two others which are related, we use similar techniques, are authentication and integrity. Integrity is about if we send a message from A to B and someone in the middle changes it along the way, can the receiver detect that that change was made? If they can detect the change was made, then we can maintain integrity. If a change can be made without the receiver knowing a change was made, then that's a compromise of the integrity of the data. Authentication is about if someone sends us a message pretending to be A, but they're actually the malicious user, and we think it's from A, then that defeats the authentication service. We want to be able to be sure that the message came from A, not someone pretending to be A. So we'll look at how encryption provides those services as well. So we'll look at some variations on this where The malicious user doesn't just intercept the message, but they may intercept and modify the message. And we'll try to see if the malicious user can modify the message without B detecting that it was modified. If they can, then that attack is successful. Let's go through some scenarios. We'll draw this again. Same scenario, user A, user B, we start with a transmitted plain text and a corresponding transmitted ciphertext, which is obtained by encrypting with KAB. We're sending from A to B still, the plain text, and we transmit that. We transmit CT. Now, let's have the malicious user intercept this message before it gets to B, not just let it go through, but intercept it and try to make a change to that message, with the hope of sending a message on to B, and B thinks it's the original message from A, but it's in fact a modified message. Let's see if that's possible. So what happens now is the malicious user gets a copy. What can they do when they receive CT? Can they read the plain text? Can the malicious user read the plain text when they get the ciphertext? No, we just saw in the previous case they cannot. It's encrypted, they cannot get the plain text. But they could try to make up some different plain text and encrypt that and forward it on to B with the hope that B thinks that was the message from A. Let's try that and see what attack may be possible. Let's say that the malicious user gets this ciphertext and modifies it first. And send the modified version onto the user B. That is, the modified one I'll denote as CT prime. That mark up the top, prime, just to say that they've changed the ciphertext. Maybe the ciphertext was a million bits, they changed some of those bits to try to perform an attack. Let's see what happens. Where CT prime is different from CT. Different values. We send it on to B. B receives some ciphertext. I'll denote that as CR. From B's perspective, it's received some bits, some ciphertext. What does B do next? Decrypt. All right, you receive ciphertext, you decrypt. You decrypt what you receive. Decrypt using a key, CR, and we'll get some value. I'll denote as PR. What key do I use to decrypt? KAB. I received a message from A. I think it's from A. The from message, the from field in the message says A. I am B, so I use key KAB. What happens at B now? It gets the wrong plaintext, or it gets recognizably wrong plaintext. That assumption is, which number? It's maybe not captured here directly, but it's based upon A7. If we use the wrong key, we'll get, it's a variation of A7. Here is if we, we're using a different key, or in fact it was a different ciphertext, in fact. We'll get the wrong, recognizably wrong plaintext. Because CR is the same as CT prime. CT prime is different from CT. Okay, we're trying to decrypt the wrong ciphertext here. So we're going to get some plaintext that is different from PT and recognizably wrong. So what will happen B recognizes that the plain text that they get from that decryption is wrong. It's just random characters. They expect some English message or some structured message. They decrypted using the key some ciphertext which was not obtained from an original structured plain text. It was a different one. So B recognizes that PR is wrong. So I think the assumptions we've got, we really should have another one that is a variation of A7, is that slightly different. Here we say decrypting with the wrong key, but in the same way, if you decrypt different ciphertext, the wrong ciphertext, you will not get you'll get a different plaintext. Decrypting two different ciphertexts will give two different plaintexts if you use the same key. Because CR is different from CT. B recognizes the plaintext is wrong. It looks like random characters, it's not a structured message, and therefore has detected something's gone wrong. They don't trust the plaintext, they discard it. So that's a case where the attack, the malicious user tried to modify something, is detected. We don't know how they modified it, but we know something went wrong, so we discard what we received. We don't trust it. We'll try some variations. What could the malicious user try to do such that B doesn't detect that? There are a couple of other choices. What could you try? Today's your chance to put on your malicious hat, your black hat. Try to do some bad things. What could you try to do as a malicious user so that B doesn't detect a change? Changed what? We could try to change the plain text. That's effectively what we did there. If we modify something here, let's say we choose a new plain text, encrypt that with a key, the key of the malicious user, and send the ciphertext on to B. Similar issue as before. If we have a new plain text by the malicious user, then the key that was used to encrypt cannot be KAB. Let's try that one. So the application of these assumptions is to apply them to use some logic to see how they can be used to provide the services. Malicious user. They choose some new plaintext, PT prime, different plaintext. They want to send this plaintext was decrease the malicious user's salary by 10,000 baht. They change it to increase. So they try to have a new plaintext and try to fool B into getting that. They choose a new plaintext and they encrypt that new plaintext with a key. And get a new ciphertext. What key do they use? Or maybe an easier question, what key do they not use? They cannot use KAB. They can use some other key, we'll denote as key of the malicious user, but it's not KAB because they don't know that. They get some ciphertext, and because it's a different key, we'll assume that the ciphertexts are not the same. CT is not the same as CT prime. We send that on. That is, we send CT prime. User B receives that. They receive CR, which is in fact the same as CT prime. They receive that and try to decrypt. What key do we use to decrypt at user B? KAB. We all still think it's from A. When we decrypt CR, well, in fact, it's the same as CT prime. We could rewrite that as decrypting with KAB, CT prime, the different ciphertext. Here, CT prime was obtained by encrypting plaintext with K of the malicious user. Here we try to decrypt with the incorrect key. Encrypted using K of the malicious user. We try to decrypt with a different key. Our assumption A7 says if you try to decrypt with the incorrect key, you'll get the wrong plaintext and it will be recognizably wrong. It'll be random looking. Again, B gets plaintext. PR. I say PR is wrong. Attack detected. If we get plaintext that doesn't make sense, then we detect that something's gone wrong. We don't care what specifically went wrong, but something's gone wrong and don't trust the message. So the use of encryption not just provides confidentiality, but also provides protection against modification attacks. This is the attacker trying to modify the data, and it provides the data integrity service. Data integrity is that if something's modified, we can detect that. And that's what's happening here. The previous case was one where they just tried to modify the ciphertext. This is effectively the same. They produce a new ciphertext. B detects that because we're using a different key to decrypt. Is there anything else the malicious user could try to do without knowing KAB? I think if you try to consider all the scenarios, you will not find one where they can fool B, because B will always detect. They need KAB. If they want to modify something, They could choose a new plaintext. If they did have KAB, then they could fool B into getting the modified message. But they don't have KAB, so therefore they cannot fool B into receiving that modified message. So this is providing data integrity. The last one we'll do is providing authentication. That is, let's try to do a masquerade attack. The malicious user will pretend to be A. We've got user B. Start again. User B. There is no user A here. We'll start with just the malicious user. What they do is they send a message to user B. They choose their own plaintext message. Let's just call it P. They encrypt that with a key and get some ciphertext and send the ciphertext to user B. But they say that this message is from A. What key do they use? Let's make some more space. Sorry. What key are they going to use to encrypt? The malicious user is going to use KAB. How? They don't know KAB, remember? User A knows, so we're not user A here, we're a different user. User A knows KAB, user B knows KAB, but the malicious user does not. But they want to pretend to be A. So they have a message, they want to pretend to be A, they encrypt it with a key, but again, they cannot encrypt with with KAB. It must be some other key. If they did have KAB, they could perform an attack. They encrypt with some other key, they get some ciphertext, send the ciphertext to B, and as before, B does the normal decryption steps. Decrypt using which key? If we think the message is from A, we decrypt with KAB. The ciphertext. I'll say we get some plaintext P prime. Is P prime equal to P? Malicious user chose a plaintext, encrypted it using K of the malicious user, obtained a ciphertext, sends the ciphertext to B, pretending to be A. A therefore decrypts with KAB, a different key. If we decrypt the ciphertext with the wrong key, we get the wrong plaintext, a different plaintext. Therefore P prime is different from P. They are not the same. And are they the same? No. And the assumption, decrypting ciphertext using the incorrect key will not produce the original plaintext. They're not the same. And the decryptor will be able to recognize that this plaintext is wrong. The plaintext will be unrecognizable output. So P, we say, is wrong. Attack is detected. B detects that what it's received is wrong and discards it. It doesn't trust it. So this is a masquerade attack. The malicious user is masquerading as A. pretending to be A, send a message to B, B detects that, and therefore the authentication service is provided. B can authenticate that this message is not from A. They can confirm. So we could use such a technique, so when you send me emails, I can confirm who's the original sender, or if it's someone pretending to be someone else, if we use this form of encryption. There are maybe small variations that we could try. I think if you work through them, you'll see that there's no way that the malicious user, without knowing KAB, can do something and have B fooled into thinking it was from A. And that's what we need for integrity or authentication. You need to look at these problems logically now. You don't need to understand how the algorithms were, but you need to follow the logic and apply those assumptions to see why we provide these services. Any questions? Okay, at the back. Yeah? The first attack, the malicious user changed the ciphertext. The ciphertext was intercepted. Let's say the ciphertext was a 1 megabyte file. The plain text was a 1 megabyte file. It was encrypted and produces a 1 megabyte of ciphertext. When you intercept it, it looks like 1 megabyte of random bits. A good encryption algorithm will take the plain text and produce random looking output. So the attacker sees 1 megabyte of random bits. They don't know what it means. They can't get the plain text, but they can modify it. Just change some of the bits. So you can modify the ciphertext. Okay, in the first one, and I don't have it here, we can modify the ciphertext, but the point was that B detected it was modified. So the modification attack, and the same with the masquerade attack, easy to do, easy to try from the attacker's perspective, hard to stop them from trying. They can try, but it's possible for B to detect that they did it. The detection acts as a security mechanism. Since we detect that they modified it, then we know, don't trust this message. All right, so we can modify anything. You send a message to someone, I intercept before it gets to them, I can change it, but the receiver will detect that I've changed it and therefore not trust that message. And that forms a security service. Any other questions before we look at some other techniques? Still on authentication. Try to stay with us through this lecture because these are the key principles, and I see some tired faces, but these are the key building blocks of what we use how we use many of the other IT mechanisms, IT security mechanisms. Let's return to the slides briefly. And we will not say too much about the things that we've missed. So some topics in this cryptographic slides we'll skip over. We've talked about attacks and brute force attacks. We've talked about the speeds yesterday. The assumptions about what the attacker knows we've covered. We said the ciphers operate on small blocks, 64 bits, 128 bits. They encrypt a block at a time. The ways to take a large file, split it into blocks, encrypt the blocks and combine them back together to get the final encrypted file, there are different methods. They're called modes of operation. We will not cover them, but if you use some of the software in some assignments, you may need to be aware or at least know that there are different modes of operation. And the list of common ones you'll see are listed here. ECB, CBC, CFB, OFB, CTR, and there are others, are ways to deal with a large file and how to break it into blocks and encrypt the blocks and join them back together. There are different approaches for doing that, which we will not look into in this course. There are also stream ciphers. Block ciphers usually encrypt 64 bits or 128 bits at a time. Stream ciphers usually encrypt a byte or even a bit at a time. They use different algorithms, but we will not look at them either today. Let's keep moving. RC4 is a popular, or was a popular stream cipher used in Wi-Fi, but has some flaws in it. So we've looked at using encryption to provide confidentiality, making sure no one can see our message. And we've just seen some cases of using encryption to provide authentication and data integrity. That is, no one can modify our message without it being detected, or no one can send us a fake message without it being detected. There are other ways to provide authentication, not just with symmetric key encryption. There are different ways for providing authentication. So just to recap, when the receiver receives a message, they would like to verify that the contents of the message haven't been modified along the way. So make sure nothing's been changed, and that the source of the message is who they claim to be. No one's performing a masquerade attack, or so we can authenticate the source. Are the general aims. There are different ways to do that. We saw some cases using symmetric key encryption to do this, provide this authentication service. But there are other approaches that use message authentication codes, MACs, use hash functions and symmetric key encryption, and public key encryption. And we're just going to look at one more of them, which is using the last one, public key encryption. And it leads us to an important concept called digital signatures. Right? So we're not going to look at message authentication codes. They're available. We will need to look at hash functions to understand digital signatures, but just the basic concepts. But so what we'll do for the rest, how long we got left, not long, we'll introduce the basic concepts of them and public key encryption. I think we'll go direct to public key encryption, and that will be enough for today. So let's jump through to public key encryption. Symmetric key encryption, encrypt with a shared secret key like KAB, decrypt with the same key. Right? That was symmetric key encryption. The keys are the same on both sides. The other approach, what's the opposite of symmetric key encryption? What's the opposite of symmetry? Asymmetry. Asymmetric encryption, encrypt with one key, decrypt with a different key. So they're different on both sides. And the other name for asymmetric key encryption is public key encryption. Right? So it has different names, and we'll see why shortly. Symmetric key encryption was used from maybe 2,000 years ago up until maybe the 1950s and 1960s, and still used today. But in the 1970s, maybe, around that time, people discovered a new approach, or designed a new approach called asymmetric key encryption or public key encryption. And different people had a large influence on that. Diffie and Hellman. We'll see there's an important algorithm, the Diffie-Hellman key exchange, developed an important public key encryption algorithm, or public key algorithm. And another one by Ravesh, Shamir and Edelman developed what's called RSA. RSA is a public key encryption algorithm. So these are some important algorithms that we'll see used in practice later in the course. So today let's just talk about the concept. Symmetric key encryption algorithms use the same key for encryption and decryption. Asymmetric algorithms use one key for encryption and a different but related key for decryption. In symmetric key encryption, if I ask you to choose a secret key, how would you choose that secret key? Guess first. Let's be a little bit more scientific about it, or a little bit more precise. How do you think you should choose your secret key? Guessing? All right, I think of a number between 1 and 10. Well, now we need a 128-bit number. So what are you going to do to choose a secret key? Probably you'll use a computer to generate a random number. All right, you'd like a random value so that someone else can't guess it. If you guess it, or if you try to write one down, most likely after you get to 10 or 20 bits of writing them down, you'll be lazy and make the rest all ones. Okay, so you want a computer to generate your shared secret key to be random. So shared secret keys are random. So what normally happens, you want to communicate with me, maybe you generate a random key of 128 bits and somehow tell me that value. Maybe give it to me on a USB flash drive or some other mechanism, and then I can decrypt what you send me. That's symmetric key encryption. The keys are normally random. In asymmetric key encryption, we have two keys, encrypt with one, decrypt with the other, but they're not random. We actually use an algorithm to generate the keys. So there's a key generation process, because the two keys must be related in some way. If they're not related, it won't work. And the general way that we use the algorithms is we encrypt with one key and decrypt with the other. One of the keys we'll call a public key because anyone can know it, even the attacker. The other key will be a private key because only one person will know that, the person who it belongs to. No one else can know it. So we'll encrypt with one key and decrypt with the other, where one of them can be publicly known, the other must be secret or private. So we talk about a key pair, a public-private key pair. And it must be hard for the attacker, given the algorithm, the ciphertext, and one of the keys to derive the other key or the plaintext. So let's maybe list, all right, first the keys. So now we'll talk about a key pair, a public-private key pair. And instead of using K to represent the keys, often we'll use PU and PR to identify the key as a public key or a private key. So it's still a key, but we're using different notation here. And we'll talk about every user in the system has their own pair of keys. User A, for example, has a pair of related keys, PUA and PRA. And every other user would have their own key pair. And if you have your key pair, the private key you must not tell anyone. It must be private to you only. The public key you can tell everyone. By the name, it's public. So the public key is available to anyone. The private key is secret, only known by one person, the owner of that key. And everyone has their own key pair. And in general, the keys are used, one is used to encrypt, the other to decrypt, and the order in which we use them, one provides the confidentiality service or secrecy, and one provides authentication. Let's see those two in use. Here we want to provide confidentiality. So A is on the left, B is on the right. A wants to send a secret message to B. Every user has their own key pair. User A has a key pair, PUA, PRA, and user B has its own key pair, PUB, PRB. So every user now we assume has a pair of keys to themselves, and users know other users' public key. That is, if I have a key pair, PU Steve, PR Steve, I can tell you what my PU Steve is. I can tell everyone what it is. I can write it on the board or send it in an email. It's public. But the private value I must keep secret for myself. So in this case, we want to send a secret message from A to B. What we do is we encrypt, user A encrypts that secret message. Now we're using M for the message. We've already used P in the name of the key. So that message M, the plain text, is encrypted, and we use the public key of B to decrypt. Right, I want to send a message to B, I use the public key of B to encrypt that message. So the ciphertext is obtained by encrypting the message, the plain text message, using the public key of B. We send the ciphertext to B, and decryption takes place using the other key in the key pair. Decrypt that ciphertext using the private key of B to get the original message back. And if the algorithms are designed correctly and considered secure, and there are algorithms that are considered that way, then no one else can discover the plaintext message. Why? And assuming no one can discover the private key, again, same with the secret key, no one can guess it. If we encrypt using the public key of B and send ciphertext, if someone intercepts the ciphertext, what can they do? Can they decrypt it? If you are malicious and intercept the ciphertext C, how do you decrypt that? How would you decrypt the ciphertext C? You know the ciphertext. You know the algorithm. We always assume you know the algorithm. So to decrypt the ciphertext C, you need the private key of B. Does the malicious user know the private key of B? No. By definition, the private key of B is only known by B. In other words, only B can decrypt, because only B has that key. And that provides confidentiality. We send the message to B. The only person in the world that can decrypt that, if the algorithm is secure, is the person that has the private key of B. By definition, that is B. Any questions on confidentiality with public key encryption? Who can send a message to B? Anyone can send a message to B, because they just need to use the public key of B. Right? And that's public. The malicious user knows the public key of B, so they could create a message and send it to B, but no one can decrypt that message except for B. And the sender, of course, knows the message, they created it. So anyone can send a message because the key is public, but that's okay. What we want to stop is that someone intercept the message and read it. And that's impossible if we have a secure algorithm and that if we don't know the private key of B. So that's how we provide confidentiality with public key encryption. Only the person with the private key can successfully decrypt. This is a different aim. Here we want to send a message from A to B such that B can verify that the message came from A, not from someone pretending to be A. We want to authenticate the source. Last slide for today. Again, every user has their key pair, PRA, PUA, similar with B. When A wants to send a message to B, we don't care who reads the message, we just want it to be sure from the receiver's perspective that it did come from A. So what we do, we take the message, we can encrypt that message using the private key of A as the key. We obtain ciphertext, we send the ciphertext to B, we decrypt using the corresponding public key. If it was encrypted with the private key of A, decrypt with the public key of A, and we get the message back. Can a malicious user intercept and see the message? Think about it. What would happen if you're the malicious user, you obtain the ciphertext. Can you see the message? Yes and no. Anyone else with a different answer? If we are a malicious user, we intercept C. To decrypt this, we need to know the public key of A. Do we know the public key of A? Public means everyone knows it. Yes, we do know it. So the malicious user does know the public key of A, therefore they can decrypt this. So this example, we're not trying to keep the message secret. I don't care if the malicious user sees the message. If I care about that, use the previous approach. This approach, I want to make sure that B can verify it came from A. Can a malicious user send a message to B pretending to be A? What do they need? I'm a malicious user, send a message to B pretending to be A. What B is going to do is they're going to decrypt with the public key of A. It will only successfully decrypt if the message was encrypted with the private key of A. Who has the private key of A? A does. The malicious user doesn't. Okay, so this is the service we're trying to provide. Stop someone sending a message to B pretending to be someone else. And that achieves that if we have a correct algorithm, because the message must have been encrypted with the private key of A such that it was successfully decrypted with the public key of A. If I receive a message from A, or claiming to be from A, I will verify it by decrypting with the public key of A. If it wasn't encrypted with the private key of A, I will detect something's gone wrong. If it was encrypted with the private key of A, it was successfully decrypted and I know it came from A. This is authentication, proving that the message came from a particular source. So be careful. These two have different aims. Confidentiality, keep the message secret. Authentication, prove that the message came from A, but not keep the message secret. If you want both, you can join them, in fact. Try and get your head around the concepts of public key cryptography and at least start to remember that there are pairs of keys. For confidentiality, encrypt with the destination's public key. See, encrypt with B's public key. Authentication, encrypt with the source's private key. Get the ordering correct, and it will start to make sense as we go through how we use these for digital signatures next week.